Welcome to this explainer. Today, we're taking the complex chemistry of carbohydrates and turning it into a fascinating story about the energy that fundamentally powers life on Earth. I am absolutely thrilled to guide you through this, because by the time we finish, you aren't just going to memorize formulas. You'll actually see how nature brilliantly captures, builds, and stores energy. Let's dive in.
Here is our roadmap for today. We'll quickly cover the plant energy story, classifying the family, simple sugars and carbons, joining units with glycosidic linkages, comparing our energy vaults, starch versus glycogen, and we'll wrap it all up with an exam prep summary table.
All right, Section 1, the plant energy story, from sun to sugar. Humans have recognized the incredible power of simple carbs for centuries. Take a look at this quote. Ancient Ayurvedic Vedas have used honey as an instant source of energy for a really long time. And it makes total sense, right? Simple sugars provide an immediate energy currency that our bodies don't even have to work hard to break down.
To track this energy story in plants, you can basically think of it in 3 elegant steps. First up, plants generate simple sugar, specifically glucose, as their base energy currency. Next, they take those sugars and construct really robust structural walls using a complex carb called cellulose. And finally, they need a way to lock away their excess energy for a rainy day, so they pack the remaining sugar into incredibly dense storage vaults, which we call starch.
Moving right along to Section 2, classifying the carbohydrate family and mapping out these molecules. Take a close look at this flowchart. Carbohydrates aren't just categorized at random. Scientists classify them strictly based on their degree of polymerization. That's really just a fancy way of saying we look at exactly how many individual sugar units are chained together to figure out which branch of the family tree a molecule belongs to. As you can see, the classification is beautifully straightforward. Monosaccharides are the absolute simplest. They contain just one sugar molecule and literally cannot be hydrolyzed or broken down any further. Link 2 of those together, boom, you have a disaccharide. Anywhere from 2 to 10 is an oligosaccharide. And once you start linking 10 or more into these massive long chains, you get polysaccharides. Section 3. Simple sugars, carbon counts, and our fundamental building blocks. Now, zooming in on these simple sugars, we define them primarily by their functional groups. If your monosaccharide contains an aldehyde group, it's known as an aldose. If it rocks a keto group, it's known as a ketose. That is step 1, your first major distinction when examining a simple sugar's chemical structure. And this illustrates our second major distinction, how we name them based on their carbon atom count. It progresses so logically. A 3-carbon sugar is a triose, 4 carbons make a tetrose, 5 is a pentose, and 6 carbons give us a hexose. So think about D-glucose, the most abundant carbohydrate in nature. It has 6 carbons and an aldehyde group. Put those terms together, and D-glucose is an aldohexose. Pretty neat system, right? Okay, so a massive point for your exam prep is understanding reducing sugars. A reducing sugar is a carbohydrate with free aldehyde or ketone groups capable of chemically reducing Tollens reagent and Fehling solution. The key word here is free. Keep that requirement in mind, because as we start linking these simple sugars together, they can actually lose those free groups and become non-reducing sugars. Which brings us right to Section 4, joining units and building the chain with glycosidic linkages. This begs an essential chemistry question. What actual mechanism locks these tiny, simple monosaccharides together into those massive disaccharides and polysaccharides we just mapped out? Well, the answer is a glycosidic linkage. Notice the critical oxygen atom bridging the gap right in the middle of this sucrose molecule. That little oxygen bridge joins an alpha-D-glucose unit on the left to a beta-D-fructose unit on the right. That specific connection, that is your glycosidic linkage. Here's a super simple analogy to help you remember how this bond actually forms. Imagine 2 people coming together to join hands and form a strong bond. But to successfully clasp hands, they first have to drop a water bottle they were holding between them. In carbohydrate chemistry, that dropped water bottle represents the crucial loss of a water molecule. So, a glycosidic linkage is formed by the loss of water between 2 monosaccharide units. Just remember the dropped water bottle. All right, Section 5, energy vaults, starch versus glycogen, and how we store the currency. Comparing these ultimate energy vaults side by side really reveals nature's incredible design. On the left, we have starch. This is the primary storage polysaccharide of plants. It's a polymer of alpha-glucose made of 2 distinct parts: amylose, which is unbranched and makes up 15 to 20%, and amylopectin, which is branched and handles the remaining 80 to 85%. Now look on the right at glycogen.
Glycogen plays the exact same vital energy storage role, but it is found exclusively in animals. That's exactly why you'll often hear it referred to as animal starch.
Finally, Section 6, your exam prep summary table.
This table right here perfectly structures your key exam takeaways. We track our molecules starting from glucose, a simple, reducing monosaccharide. Next is sucrose, a disaccharide joined by that glycosidic linkage we talked about. And notice, it is non-reducing. That's because the linkage literally ties up those functional groups. Finally, we reach our massive polysaccharides, starch for plant energy storage and glycogen for animal energy storage. And yep, both of those are completely non-reducing as well.
As we wrap up this explainer, I really want to leave you with this one remarkable thought. The next time you sit down to eat a bowl of rice or maybe a baked potato, just think about the molecular engineering happening inside you. How exactly is your body going to disassemble hundreds of thousands of alpha-glucose units locked inside those plant starch faults, break all those glycosidic linkages, and then expertly rebuild them into your very own vital glycogen energy